5 minutes of convolutional neural networks. There's no such thing as 5 minutes of CNNs, but I just want to introduce this to you, just to give a sense. Because CNNs were the first deep learning models that became super successful. They were for image classification. We can think about why they would be so good, why a simple convert it into a bit vector and run a fully connected neural network will not be the best idea. Okay. Again, the old style model was, give me the image, I will convert it into a set of features. Give me the audio, I'll convert it into a set of features. That doesn't happen anymore. You give raw images, and that with the learning algorithm makes the feature representation. Now, here is the question for you. Suppose I am giving you the 16 cross 16 bit vector, which says A. Let's take an easy one, which says 1, right? Now this 1 could be right in the middle, very, very vertical. This 1 could be slightly slanted, still in the middle. This 1 could be slightly shifted, but vertical, right? We need to make those predictions, all of them correctly. Whether it is right straight here, whether it is slightly slanted, whether it is slightly shifted, whether it is slightly shifted like this, whether it is this kind of a 1, whether it is, there are different kinds of 1s as well. Now, technically, there is the universal approximation theorem. Technically, even a 2D, a two-layer neural network can do this. Technically, a fully connected neural network can do this. But let's figure out at least some parts of the structure of the problem. Let's figure out, what can we say about our problem at hand, which allows us to make some improvements in the architecture. So how do we even start thinking about this? So the intuition that they came up with is that let's come up with invariances. And there are many kinds of invariances. One is called the translational invariance. Let's say I translate every pixel right. So I had a 1 like this, now I have a 1 like this. It shifted. Is it a 1 still? Absolutely. It is still a 1. Or I shift it left, it's still a 1. I reduce the size, it's still a 1. I blow it up a little bit, it is almost still a 1. I rotate it slightly, it is still a 1. I rotate slightly in the other direction, it is still a 1. But I keep rotating it, is it still a 1? No, this is not a 1. So, people were like, okay, so what kind of invariance are we absolutely sure we need? Well, translation invariance we are pretty much sure we need. That if my eye was exactly in these locations, or it was in these locations, or slightly shifted, I still care, right? It's still okay. So they said that let us create an architecture which imposes that whether you give me the original image or you give me a slightly shifted image, I will still make the same prediction. Now that won't be true in a bit vector representation, because every bit is defined and separate. But here we are saying that if the structure is shifted, we should still be okay. We should be able to deal with it. So for that, they came up with this general principle of convolution. So what does a convolution do? It takes the original image, this is my original bit vector image, and it takes a filter. This is called a filter. Now these filters are very common. Have you used any kind of image editing software? I'm sure you have used Photoshop or Irfan View or whatever, some photo editing softwares, whichever is your favorite. You must have seen a lot of filters, low pass filter, edge detection filter, this filter, that filter. What is that doing? Well, it is nothing but an element-wise multiplication with an addition. So let's say my filter is 1010101001, this filter. I will apply it to each 3 cross 3 subset, not subset, but subsequence, right? Sub-image. So when I apply it to the very first image here, it will be 1 times 1 plus 1 times 0 plus 1 times 1, and so on and so forth, and I will multiply these 9 numbers with these 9 numbers and add them. I will get a 4, because this, I believe this, and this, and this. These 4 terms will contribute. So I will write down the number 4 here. Then I will shift everything by 1. I will still do the same. I will write down the number 3 here. And I will keep doing this. So if I had a 5 cross 5 image and I had a 3 cross 3 filter, I will get a 3 cross 3, a convolved feature image or feature matrix, whatever. What is the intuition? The intuition is that this is a convolution. Think of it as a feature. Why do I say think of it as a feature? Because people have studied many kinds of filters in the past. If I run every image by this original identity filter, I get the original image back. But if I run it through any of these, I get edge detections. Can you see? These are the edges that are getting detected, depending upon what feature values we have. I can also have a sharpen filter, which makes all the edges sharper. I can have a blur filter, which makes all the edges blurred. In fact, there were computer vision researchers or image processing researchers which did this for a living. They will come up with new filters and they will show the effect of those filters on the images. So therefore, think about it. What is it saying? It is saying that applying a filter is like finding a feature in that image, in that point, in that subspace of the image. And because I am doing it for every part of the image, I will come up with slightly smaller image, but which will have a lot of features. It will have, the number will indicate whether the feature is present or strong, or negative number will indicate that it's absent or weak or opposite, has a negative influence, and so on and so forth. But I don't have to do just one filter. I can do many such filters. These are, by the way, called convolution filters. I can do many such convolution filters. Each filter creates an image of numbers. Many filters creates many images of numbers. You can again think of it as, so what is an original image? An original image is technically X cross Y cross RGB values. So you can say 3 channels, R channel, G channel, B channel. Now after I do a convolution, I will have a 2D image with one filter as one channel. Then if I have many filters, I have many channels like this. So basically I convert some X cross Y cross Z image into an X cross Y cross Z image after doing lot of convolutions on top of it. And when you train this automatically for object detection, these are the kinds of filters you learn for layer 1. Let us look at, this is the filter you learned for layer 1. This is sort of saying, do I have a slant line pointing downwards, right, to the right? Do I have a slant line pointing downwards to the left? And so on and so forth, right? More oblique line, a horizontal line, and so on. And this feature is on for these kinds of images. This particular feature is on for these kinds of images, and so on and so forth. Notice that for object detection, I am learning the very low level information in the first layer. What happens in the second layer? I learn slightly better filters. Notice that I am learning like a full round thing here in the middle, right? I am learning more interesting shapes because now I can combine these together. If I keep doing this in layer 3, you can see that I am starting to learn some textures, some mesh patterns, right? These kinds of textures correspond to this kind of, let's say, tiger skin or things like that, right? You can have more interesting combinations. Yeah. Then if you go to layer 4 and layer 5, look at layer 4. In layer 4, I am almost starting to learn dog faces here, right? Small nose, 2 eyes, you know, this kind of a structure. I can start to learn some dog faces. I can start to learn more interesting patterns. And finally, I am able to learn the entire objects with significant pose variation. So it sort of gives you the handle that if I put in this filter on the input, create another image, that learns some useful information, then I create more filters on that as input, then I create, you know, next level features, more next level features, more next level features. So I can keep doing layer by layer convolutional neural network. Now, is this translation invariant? That's a question you should ask. And that comes in because of max pooling. Now what does max pooling do? Max pooling says I will take these two and I will just convert it into max. I will take these 2 cross 2 and I will just take a max and convert it into a 1 cross 1. So now what am I saying? Irrespective of whether my 6 is here, here, here or here, I will still output 6. In other words, it is saying that I will keep the strongest influence irrespective of where it was in this small subimage. And I will do it at every phase. So I get small local translation invariances. So my final scene in architecture becomes something like this. Do a convolution layer, then do a max pooling. This is called max pooling. Do another convolution layer, then do a max pooling. Do another convolution layer, do another max pooling. And every time you do this, you are reducing the size of the image. Finally, you are left with a very small image, maybe 1 cross 1 image, but there are many channels, so you are left with a big vector, and then you can run it through a fully connected neural network to make the final output class prediction. Now the biggest problem is, how do we figure out what should the filters be? I just showed you some filters that humans had created. But what do I do? Which filters do I use? Any guesses? We don't give any filter. We let the algorithm learn it. What is a filter? It's a matrix. It's a matrix of parameters. Let us define this matrix of parameters as free parameters. And let's just take derivative with respect to those free parameters and back propagate. And this is going to be a very interesting way of thinking down the line. You think of an intuition. You say, okay, if I have this kind of a matrix, this will do this. If I have that kind of a vector, it will do that. You define it as if you were doing it. But then you leave your hands out and say, okay, I'm not going to give the features. I'm only going to give the structure of features. The structure of features is that I will do convolution and they will have this 3 cross 3 weights or 4 cross 4 weights or whatever it is. But then the model will learn it completely independently. So we gave it the structure for the features, which is a filter, but the model figured out which filters, which features were necessary for the task at hand. And here are the results. I believe I have shown you this slide on the ImageNet dataset. It's an object recognition dataset. In this object recognition dataset, we have an aeroplane class, an automobile class, a bird class, a cat class, a deer class, a truck class, and we have lots of examples. It's a large dataset. And I had told you that until 2011, the non-neural solutions, the state of the art was 25% error. When AlexNet came in 2012, I believe, it showed, and every year they would make improvement, and the improvement would be 2.2 points, 0.4 points, extremely small improvements. The field was moving very slowly. The errors were going down very slowly. The first time AlexNet came from the University of Toronto, it brought the error down to 16%, a jump of about 9%. People were shocked. People could not believe it. People were like, this is not possible. But they figured this out, they started working pretty fast, and then every year new architectures came, which basically went deeper and deeper. I believe ResNet is 156 layers, so I could be wrong in my exact number. And finally, I am told that the human performance on this task is about 2%. And we have been able to beat that. Oh, 152 layers, it says it on the slide. Now, beating humans in this dataset does not mean that image recognition is solved or object recognition is solved. No. It only knows these classes and no other class. Right? It cannot learn a new class quickly. If I showed you the seagull for the very first time in your life, but you have seen many other birds, how many data points would you need to learn what is a seagull? How many birds would you have to see to learn what is a seagull? Jay says 1, somebody says 2, nobody has said 3 so far. You have so much conviction in your ability to learn what a seagull is that you think 1 or maximum 2 examples of a seagull and I would figure it out. And you are probably right. Do you think how many examples of a neural networks will need to learn a new class? Thousands maybe. So we have not solved the problem. By the way, this is called zero-shot learning. Sometimes I don't even show you a seagull. I just say that a seagull in English. I say a seagull is like is a white bird with a fat this and a long beak and blah. I just give the description, and maybe you won't be able to recognize seagull, but there's some chance you would be, without even seeing the first seagull in life. Right? If you think about our medical professionals, people who do surgeries, you every once in a while come up with a rare abnormality. Have you been trained on that abnormality? No. You have never seen that in life. You may have read it in the book. But because you have read it in the book, when you see it, you can make the connection. Our machines cannot do this, right? So there are a lot of things that our machines cannot do in computer vision today. So vision is not a solved problem, but the amount of progress we have made is by leaps and frogs. Yes, there was a question. Right, so Path says that I might see, if I see a seagull in practice, I will see them like a video, not like an image. But I can show you images also. I can do the test where you have to learn a new concept and I am showing you images only. And then it's equivalent to a machine, right? It's not very different. But yes, you can also do a video, and I'm not sure that our machine will be very good with videos either, right? So I think this is a good time to stop today. We are left with one small part of this topic, which is deep reinforcement learning. So now what have we done? We have learned how to approximate a function, but we have not learned how to use it in reinforcement learning. Now that's a full course in and of itself. Just deep reinforcement learning is a full course actually, believe it or not. But we will cover 10 minutes of that at the beginning of the next class to complete the story that we started some time back. With the RL class. After completing that story, that would be the last mathematical thing that we will study. And then we will move into ethics of AI. We will talk about if AI systems are really becoming that successful as they are, they will start showing up in our world, in our real world very soon. And what are the challenges that we will need to solve in order for them to be successful in different applications. Where is it a good use of AI? Where is it not a good use of AI? Would AI lead to better fairness or worse fairness? Would AI lead to new kinds of mistakes but less number of them? Would AI lead to, what would AI in our day-to-day life lead to? That is the question that we would ask, and we would discuss this in the next class. Maybe we will have a part of that conversation in the last class, and in the last class we will wrap up. So we'll go over the full course that we studied. We will talk about what have we studied, what are the take-home principles, and what is the big picture of the full AI course.